Assalamualaikum and a very good day to panels Dr. Afarul Razi and Dr. Ahmad Fateh. Thank you for spending your time to evaluate and watch my PSM1 video presentation. My name is Ainur Maisara binti Ahmad Faris and my metric number is TE190187 and my supervisor is Professor Madya IR Dr. Muhammad Saufi bin Kamarudin. The title of my project is Breakdown Characteristics of SF6 plus N2 gas mixtures under voltage impulse. Not to waste your time, now let's jump to the first slide. In this new era of the globalization, the potential benefits of electrical energy given to a multitude of users through a shared generating system which were recognized shortly after the discovery of the dynamo or generator. Therefore, electrical power supply is so crucial in today's globalized society that the quality and continuity of the supply are one of the utmost importance. A typical power system consists of three components which are the generation, transmission, and the distribution of electricity. Energy sources such as wind, solar, water, and even nuclear are turned into electrical power during generation. Power is then delivered in bulk via overhead lines or underground cable at various stages depending on the power generated, transmission distance, load conditions at the end, and other consideration. Over the last 3 decades, various insulation medium have been used, such as oil has been used as in bulk circuit breakers and is still used for cooling and insulating purposes in power and auto transformer. Meanwhile, air blast, air circuit breaker, and vacuum circuit breakers have also used SF6 gases as its insulation medium. Due to its superior insulation properties, SF6 has high insulation and excellent arc extinguishing performance, chemical stability, and non-toxicity compared to the other insulation gases. Therefore, SF6 has been the primary insulator for many high-end electrical applications, especially the switchgear insulation. However, several studies reveal that SF6 has a greenhouse effect that raises worries about its environmental impact. This concern has an impact on the global warming. As a result, SF6 is an extremely powerful infrared absorber and a greenhouse gas. Current research is focused at developing a substitute that is not necessarily superior than SF6 but has comparable insulating capability and it is less hazardous to the environment. The primary research purpose and goal of this thesis is to find a replacement for SF6 in distribution networks that may be employed efficiently in the near future. The suggested alternative is not likely to be as successful as SF6, but it should have less environmental hazards while remaining cost-effective. The objective of this project is to obtain the breakdown characteristic properties of SF6 plus N2 mixtures under lightning impulse and several factors such as electrode configurations, polarity of lightning impulse, gap length between the electrodes, pressures, and SF6 plus N2 content. Second is to determine the electric field stress for SF6 plus N2 gas mixtures in various test conditions which leads to breakdown using the simulation FEMM. Lastly, to produce relationship between gap distance with field uniformity. Some literature review have been made to support this study is Vital SF6 gas theory, properties of SF6, gas sulfur hexafluoride SF6 as an insulation gas, property required for power system application, and last but not least, physical and chemical properties of N2 which is nitrogen. Now, let's jump to the methodology part. First of all, this project will be used two methods in order to achieve its objectives, which is experimental work and FEMM software for simulation. This is the experimental work setup and will be conducted at high voltage laboratory in UTHM. First, the AC supply will be generated from the HV test transformer, then it will convert it into DC supply which need to enter full wave rectifier, then the generated DC supply will charge the capacitor to produce the impulse voltage at the spear gap. At the end of the circuit, there is two identical pairs of configuration electrodes which will be used for the experimental study with different air gap where the electrodes vertically align. The upper electrode is connected to the high voltage terminal and the lower electrode is connected to the ground terminal. Experimental work will use up and down method, which is a sequential design method for binary response variables that exist for determination of the concentration. To understand more, this is the flow chart, which we set the number of breakdown voltage at 20 times chart, which n equal to 20, using the up and down method. The voltage is then applied to the impulse voltage generator. The first shot is fired until there is a breakdown. Where a breakdown voltage occurs, the number of breakdown voltage is checked to see if it is complete 20 times or not. If the number of breakdown voltage shots is less than 20, the voltage will be decreased and the voltage will be applied again. If the breakdown voltage is completed in 20 shots, the next step is to determine the 50% breakdown voltage, which is U50. When there is no breakdown voltage occurs, the number of breakdown voltage checks whether it is completed 20 times or not. If the number of breakdown voltage shots is insufficient, the voltage will be increased by applying voltage gain. If the number of the voltage shots reach 20, the next step is to compute the 50% voltage breakdown, U50, and the voltage interval between levels for increase or decrease should be between 1.5 until 3% of the predicted value, U50. This project also includes simulation using FEMM software to obtain the electric field between the two electrodes configuration with the initial voltage value that we get from the experimental work, U50. This is the flow chart. First, we need to draw the electrodes, then define the parameter. After that, set the material properties, boundary condition, create mesh, and study the setup. If the setup is confirmed, then merge. Lastly, run the simulation and get the post-processing of the result. To understand more about the flow of the project, this is the flowchart that can be used to enhance your understanding. First, research has been made on using the up and down method to determine the U50. After that, test project in HV lab by using different types of electrodes, then obtain the U50 by determining the shots of breakdown. Next, use the value from the experimental work to simulate electric field strength using FEMM software. That's all. Next, let's jump into the initial result. In this initial result, for the experimental work, I have used sphere-to-sphere electrodes configuration with the gap of 1 cm, 2 cm, and 3 cm gap. The up and down method has been used while in this laboratory to get the U50. Below are the table for the result of up and down method. Y means yes, which at that voltage it has a breakdown, that so we need to lower the voltage and see if the breakdown can occur at more lower voltage. If not occur, then we need to write N, and then we need to raise the voltage value more than the value from the two past value. After that, the U50 can be calculated by using formula below. By adding all the value that we get from the experiment, we need to divide it by 10 shots. Since I have not so much time, so I only do 10 shots, which in rules, the minimum number for shots is 20. So for 1 cm, we get 33.32 kV, 2 cm we get 71.12 kV, and 3 cm is 103.12 kV. From here, we can conclude that the more gap length, the harder the electrodes get breakdown, because the more voltage impulse needed to break down the air. After that, all of the value will be used as boundary at upper electrodes which connected as HV. Set up the model, then run the simulation to get the electric field strength. Here is the result for 1 cm gap. The density are more at the curve of the bottom electrodes, which are connected as ground. This describes the highest field intensity spot Emax is the highest probability where breakdown may occur. Figure on the left side shows that the graph of the potential V versus gap length for both sphere-to-sphere electrodes. By referring to figure right, the voltage are decreasing from point A to B, which is the bottom electrodes does not have much voltage. From the figure from the right side, the minimum electric field occurs in the middle of the difference gap between the electrode sphere, which is around 2.9 megavolt per centimeter, and the maximum electric field occur at the point A and B, which is 4.4 megavolt per centimeter. Figure shows that the field intensity density for 2 cm gap here. From the observation, the highest field intensity value occurs at the above curve of the bottom electrode. Despite the bottom electrodes does not have any impulse voltage on it, but it has more streamer than the top electrodes. The highest field intensity spot Emax is the highest probability where breakdown may occur, such as in the previous slide. Moreover, since the gap are increasing into 2 cm, therefore in field intensity occurs at the middle of the gap difference are getting lower than in 1 cm gap. Figure on the left side show the graph of potential V versus gap length for both sphere-to-sphere electrodes for 2 cm. By referring to the left side figure, the voltage are decreasing from point A to B, which the bottom electrodes does not have much voltage. It is same as the previous 1 cm gap. From the figure right side, the minimum electric field occurs in the middle of the difference gap between the electrode sphere, which is around 2.9 megavolt per centimeter, and the maximum electric field occurs at the point A and B, which is 5.6 megavolt per centimeter. Figure here shows the field intensity density for 3 cm gap length. From the observation, the highest field intensity value occurs at the above curve of the electrode. Despite the bottom electrode does not have any impulse voltage on it, but it has more streamer than the top electrode. Furthermore, as the gap increases to 3 cm, the field intensity at the middle of the gap difference become lower than in 1 cm and 2 cm gap, as shown in the previous slide. Figure on left side shows the graph of potential V versus gap length for both sphere and sphere electrodes. By referring to the figure again, the voltage are decreasing from A to B, which is the bottom electrodes does not have much voltage. From the figure on the right side, the minimum electric field occurs in the middle of the gap difference are around 2.7 megavolt per centimeter, and the maximum electric field occurs at the point A and B is 6.5 megavolt per centimeter. In conclusion, the more gap length, the lesser the electric field intensity between the electrodes, which made it harder to break down. Table below shows the value of analysis result for experimental work by using U50, Emax value from the simulation by using FEMM software, Emax average and field utilization factor FUF for the sphere-to-sphere electrodes configuration with different gap distance 1 cm until 3 cm. From the graph below, the impulse voltage V versus gap distance can be shown as the gap distance increases, the breakdown voltage becomes more difficult to occur, and the higher impulse voltage value is required to break down the air. This is a result because the electrons being unable to restore the energy, then they collide to each other, resulting in an electron avalanche between the gap length and a breakdown. For the electric field strength, E max versus gap distance graph, that the greater the gap distance, the greater the uniformity of the electric field between the electrodes. This is due to the fact that as gap length increases, the electric field becomes more non-uniform. The non-uniformity of electric fields between the electrodes can be demonstrated when the field utilization factor decreases as the gap distance increases, as illustrated in the graph field utilization factor. As a result, the field utilization factor is inversely proportional to the Emax value. Thank you for spending your time to watching my video again. Thank you.